Hi, so I have been working on a mathematical framework for quantifying nonlinear uncertainty propagation in Eddy identification criteria. So let's start by talking about what I mean by Eddy identification. So oceanic eddies are large rotating flow structures produced by turbulence. Particularly, mesoscale eddies are highly influential on global ocean dynamics, driving the transport of momentum, heat, salinity, mass, nutrients, oxygen, biomass, and pollutants. Their role in the rapidly changing polar regions is becoming even more important in the age of climate change, and the criteria used to identify and track eddies are inherently nonlinear. There are several eddy identification diagnostics. We will focus on the most commonly used one, the OW parameter, as an example case for our framework. The OW parameter measures the strain relative to the vorticity, and negative values of the OW parameter indicate strong vortical flow or eddy formation. Most importantly, the OW parameter is a nonlinear function of the flow field velocity. The data and models used to estimate the flow field velocity inevitably have uncertainty, which can be either suppressed or amplified by the nonlinearity in the Eddy diagnostic. This framework seeks to track this propagation of uncertainty through the nonlinearity. The root of the framework lies in the simple flow field model, which uses stochastic parameterization to mimic turbulent flows, while maintaining analytically tractable statistics. These statistics are then nonlinearly mapped to the Eddy diagnostic statistics, giving us an explicit relationship between the two. On the other hand, the framework also utilizes the stochastic flow field model as a forecasting model for the Lagrangian data assimilation framework, which is nonlinear but provides analytically tractable flow field statistics. This allows us to assess the uncertainty reduction from incorporating increasing numbers of observations via information theory, both before applying the Eddy diagnostic and after applying the Eddy diagnostic. This allows us to answer several key questions. We are able to look at how the flow field statistics modulate the Eddy diagnostic statistics. And we're also able to see how the Gaussian flow field can be morphed into a non-Gaussian distribution for Eddy diagnostics. There's also spatial patterns that emerge when we apply the Eddy diagnostic. So that's what we can see from one side. Then on the other side, we are also able to see how the uncertainty reduction changes as we increase the number of observations. We are able to identify an information barrier in the uncertainty reduction as the number of observations increases, as well as the dominant components in the Eddy diagnostics for large numbers of tracers. So let's start by looking at the details of the first path and see what it's like, what we are able to get out from our framework when we apply it to the OW parameter specifically. So we're looking at the nonlinear relationship between the flow field and Eddy diagnostic statistics. So we'll start from the root of our flow field model, or the root of our whole framework, which is the flow field model. We're working with a two-dimensional velocity field on a double periodic domain, and this allows us to represent the velocity field using a truncated sum of its Fourier bases. And each Fourier coefficient follows an OU process, a complex OU process. Such a dynamical structure has been commonly used to mimic the turbulent properties, as the stochasticity compensates for the turbulent features produced by deterministic nonlinearities. It is also widely used as a forecast model in data assimilation for turbulent systems. The simple structure facilitates the theoretical study of uncertainty propagations as the statistics have known closed formulae. This is just to motivate that we can use this flow field model, and it does accurately represent the turbulent dynamics. So we're comparing our OU approximation to a quasi-geostrophic model that has deterministic nonlinearities. And our OU approximation has very qualitatively similar spatial patterns as well as temporal patterns. That's all I'll go into it for now for time. But now let's talk about how we go from the statistics of the flow field to the statistics of the Eddy diagnostic. For an Eddy diagnostic, not necessarily just the OW parameter, we can use the mean fluctuation decomposition of the velocity field and then apply our Eddy diagnostic and then take the expectation or the variance. So when we do this for the OW parameter, we get this expectation and this variance. This variance formula in particular highlights the underlying structure between the summation of the fluctuation terms, which depend completely on the variance of these different modes in the flow field, and the mean fluctuation terms, which depends on both the mean of the flow field and the variance of the flow field. Notably, although due to the global Fourier basis functions, the uncertainty in the flow field is spatially homogeneous, the uncertainty in the OW parameter is spatially inhomogeneous. Digging a little bit further into this spatial inhomogeneity and looking at the structure of these terms, we're able to identify a close link between the expectation of the OW parameter and the variance of the OW parameter. In fact, the local minima of the expectation, marked by the red dots here in both of these panels, which correspond to Eddy centers, attain the highest uncertainties. So the places where we are identifying eddies are actually the most uncertain areas. Now, let's move on to our second path that we can go down, examining the uncertainty reduction before and after applying the Eddy diagnostic. So, to measure the uncertainty reduction, we use information theory. We're comparing two different distributions. The prior distribution, which comes from purely the model, which we've already established the model has statistics that are analytically tractable. We know the statistics of the prior distribution. Now, when we incorporate observations, the uncertainty is reduced, and we have a different distribution we call the posterior distribution. To quantify the uncertainty reduction in the posterior distribution related to the prior distribution, the relative entropy is adopted. This is the general relative entropy form, and then this is for Gaussian. So in the Gaussian form, we have the signal term, which is the uncertainty reduction in the mean weighted by the prior covariance, and then we also have the dispersion term, which is the uncertainty reduction in the variance. Now, the next question is, we have the prior distribution. What is the posterior distribution? Well, in this framework, we utilize a nonlinear Lagrangian data assimilation scheme in order to have the turbulent dynamics we need to have, as well as the analytically tractable statistics. So this is our flow field model, remember. Now the observations are given by Lagrangian tracers, which follow the fluid's movement. So then the observational process of the Lth tracer is going to be given by this equation here. Now, the derivative of the displacement of a tracer makes sense that it equals the velocity, then plus some noise, which accounts for the unresolved modes not included in our set of modes. Now, it's the velocity at the location of the tracer. Now, plugging this into our Fourier decomposition, we see that this is a non-linear function of our tracer location. We can then vectorize this, and we're able to see a more compact version. And we can see that this, when we know the observations, when we know x, then this is a linear system. And thus our system is linear and Gaussian conditionally. This is called a conditional Gaussian nonlinear system, CGNS, which means that we have known closed formulae for the posterior mean and variance. So we have two different posterior estimates. The filter estimate is like real-time data assimilation. we use the observations up to our current time step. Just to give you some intuition behind this formula a little bit, this is the forecast, and then this is the Kalman gain. If the Kalman gain is constant, then you have nudging. Then we also have the smoother. The smoother mean and variance utilize not just the information up to the current time point, but also future information, future observations. So this is a post-processing step. So in general, the conditional Gaussian nonlinear systems also contain Lorentz models and Boussinesq equations, and have wide applications in nonlinear continuous time data assimilation, uncertainty quantification, and surrogate models. Recent studies have also incorporated CGNS into optimal control and machine learning and digital twins. So now we have the prior distribution statistics and the posterior distribution statistics. We want to examine this as a function of the number of tracers, the statistics as a function of the number of tracers. So let's take a look at the asymptotic analysis of the smoother covariance. Turns out it converges to a diagonal with entries given by this equation. So as the number of tracers increases, we see a decrease in the variance of each individual mode. Now, we can use this in conjunction with our analytic formulae for the OW variance and expectation, as well as the relative entropy formula, in order to see the uncertainty reduction in both the flow field and the OW parameter. So the signal part of the uncertainty reduction converges to a constant as the number of tracers increases. However, the dispersion part converges to a function of the ln of L. So in order to reduce a fixed amount of uncertainty, an exponential increase of the number of tracers is needed. When L becomes larger, the information reduction by each new tracer is less and less, which demonstrates a practical information barrier. So in whole, the mathematical framework is developed for modeling turbulent systems and facilitates nonlinear data assimilation with closed forms. It is used to quantify uncertainty propagation and Eddy identification criteria where uncertainty interacts with the nonlinearity. The analytically tractable modeling and diagnostic framework allows theoretical analysis of the underlying structure of the Eddy statistics. Although due to the use of global Fourier basis functions, the uncertainty in the flow field is spatially homogeneous. The uncertainty in the OW parameter exhibits spatial inhomogeneity. In fact, the local minima of the OW expectation corresponding to Eddy centers attain the highest uncertainties. An information barrier in uncertainty reduction as the number of tracers increases in data assimilation is discovered with rigorous analysis as well. So we're currently working on the paper. It will be soon out. Please feel free to contact me at crmoser2@wisc.edu if you have any questions. While I'm not available in person today, I would be happy to chat via Zoom. More information on this and related work can be found at my website. Thank you so much for listening.